And now our next speaker, one of our prize guest speakers, please welcome to the stage Senior Performance Architect at Netflix and eBPF fan, among other things, Brendan Gregg.
Part of using a tracer, however, is what to do with these superpowers. I've given many different talks where I've discussed issues that we can solve with different tracing tools, methodologies that we can use to apply to using tracing tools. In this talk, I wanted to do something different, where I will cover how I design tracing tools and how I build tracing tools, as that may be another way to help you see how to wield these superpowers and how to apply them. Sometimes when I create tracing tools, people see them as though I'm the one with magical superpowers, the way I can create them and present insights into the system. But in this talk, what I want to do is dispel some of that magic and show that it is a routine, a set of steps that I go through for creating these tools that we can all do. I'm still developing tracing tools, so I'm currently developing them for BCC and BPF. And some of these tools I've developed for many different tracers in the past. Some of them are new, but I still have my hands on tool design. This talk will be interesting for tool developers if you end up actually designing and building tools. But it will also be useful for everyone who consumes tools. So the problem with tracers, as I mentioned, is what do we do with these superpowers? And by seeing the sort of things we can do, you know the sort of things you can ask and the sort of things you can expect from application performance monitoring systems. What I'm going to cover is applicable to all tracers. So whether it's Sysdig, BCC, BPF, DTrace, System Tap, LTD&G, I've used far too many. I've used all the tracing tools. I'll start with methodologies. And this is where I really start with coming up with tools. It's easy with a tracing tool to print out numbers. But is it useful and is it solving real problems? With methodologies, these pose the questions of the system that we would like answers for. And this is really the genesis of why I come up with tools. For methodologies, I like to start with a functional diagram, a block diagram of the system. I've got one here that shows the kernel and application, so a classical operating systems block diagram, but you may have one for the internals of your application, your distributed system. Then based on the functional diagram, I can apply methodologies. To give you an idea of how this works, I've discussed it at the system call layer, and Adam gave a talk earlier today about the importance of syscall tracing. And so here's three methodologies that I could apply to the system call layer and how they could become tools. Workload characterization. With workload characterization, I don't care too much about the resulting performance or the resulting errors. I just care about summarizing the load that's applied to the system. You'd be surprised how many performance issues are solved just because the workload is dumb. The application is doing millions of failed closes like we saw in the last lab. And once you identify that, you can then eliminate that dumb workload and improve performance, sometimes by factors rather than percents. So in terms of tracing tools, some examples I've done in the past include exec-snoop and OpenSnoop, which are really simple workload characterization tools at the syscall layer for doing tracing execs so that you can see when new processes are created and exec themselves, and OpenSnoop to see what files are being opened. Connect and accept, just seeing what connections, you can trace them at the syscall layer or higher up in the stack. And I've done tools in the past for that, which can be useful to understand network connections that are going on. Read and write size histograms. Why might they be useful for workload characterization? I've had issues in the past where you can see that you're doing far too many reads and they're very small reads. Maybe they're 1 byte reads. And you can change the application to use a larger buffer size and improve performance. Again, this is characterizing the load applied to that target, and that target is the system calls. It doesn't matter whether those 1 byte reads are fast or slow, or whether those failed closed syscalls are fast or slow. For this methodology, it doesn't. It just matters about identifying the workload. Then there's latency analysis tools, and that's a different methodology, and that's where I want to thoroughly understand the latency. And I've written many tools like this, func latency for doing histograms. Maybe you want to do read and write latency at the syscall layer. Another methodology I like to use is one I created called the use method. And that's where I look for 3 metrics in particular: utilization, saturation, and errors. And so you can imagine coming up with a tracing tool that measured those 3. It's very easy to create tracing tools that measure far too much, and you have too many numbers for the end user to understand. One of the beauties of the use method is it just picks 3 that are really useful, and then the user can understand those 3. So utilization is over time how busy that resource was. Saturation can be a measure of queue length or time waiting queued, and then errors are errors. And so I should write a tool that does network utilization by thread so that you can imagine doing this in Sysdig or any tracer where you can expose what percentage of time does this application thread spend doing sends, network sends, or network receives. Maybe it's already been done. System call errors is another use method style tool that you would think of doing if you're applying the use method to the syscall layer. So you can imagine doing those methodologies at other targets as well. So you can imagine going to the file systems layer and looking at workload characterization for file systems. What are the different file system operation types we do? So reads, writes, opens, stats, mkdirs, and so on. Latency. What's interesting there? Well, file systems can do things synchronously and asynchronously, so maybe you want to understand more the synchronous latency calls. And then for a use method of file systems, well, you could come up with errors. That one's easy, but you also may come up with interesting metrics to expose, say, utilization and any measure of saturation in the inner workings of a file system. So I hope that illustrates a little bit a methodology to pose questions that you then want to answer of the system, whether it's workload characterization, latency analysis, use method, or many other methodologies. It's too easy to get into the trap where you've created a tool, a solution in search of a problem. So I have some output, and I think, wow, that looks really interesting. Look at all those numbers, but I don't know what I'm going to apply it to. And so that's why thinking about methodologies first will begin with the questions. So to see this actually applied, I'll start with CLI tracing tools, and then I will do GUI tracing visualizations. And for the command line interface, there's 6 different templates I use. So at this point, we've got a methodology. So say I want to apply workload characterization. Now I've got one of these templates I can pick to create a tool. Now I want to talk about CLI tools for a few reasons. One of them is they have lots of uses other than solving a problem. Let me demonstrate. It should come back in a second. So earlier today, we saw Luca gave a Sysdig workshop, and it involved a lot of using Sysdig. So this is a text-based GUI. And then Gianluca did more of the chisel style at the command line. Now, I really like the command line tools that you can run. And if you want to use an interactive tool like Sysdig, that's great. But I thought I would make the case for the value of the single-purpose tools at the command line, as I'm going to go through those in the slides anyway. And I thought of this during the lab. So I'm going to cover 4 reasons why I like to use the command line versions of this. So here's the Sysdig lab. Now I can run, so here I'm playing around. So I've got my trace file, trace03. I can list all the different chisels I can run on it, and I can run the top cons. Okay, I can run spy. Do I want to do a spy or top HTTP? How about the HTTP log? That's pretty good. I can do spy users, see what users logged in. These are all in my scrollback buffer. Okay. If I run a few of these chisels, what I can do is I can scroll back and forth, and it's in my scrollback buffer. So if I'm conducting an investigation, and I start off with a summary where I've got here's my top processes that are doing networking, and now I want to look at some of the HTTP requests that they might be doing. I can scroll back and forth and maybe associate a clue over here with a clue down here. That's something that lends itself very well to the command line with the scrollback buffer. A second thing I can do here is, if I see something interesting, this all may be obvious, if I see something interesting, I can copy and paste it, and then I can share it with colleagues. I can put it in say I'm using Jira to file issues. I can paste it in there. That's also a little bit more difficult to do with, say, a GUI, like Sysdig, where you're bounded to the screen size. Not that it's bad, it's just a different way of doing it. Another way it's useful at the command line is I can type history. You can see me mucking around. And if I end up solving a problem, I can then copy and paste all of the prior commands I did and then include that in the Jira ticket or share that with colleagues as a learning exercise. If you're hopping around with Sysdig, it's really powerful and really great. But you can imagine thinking, how did I get here? Did I do function 2 and then went to this view and then I went to this view? Here you've got your entire history in the scrollback buffer. I can copy and paste things out, and I can type history, and then I get that summary. And then the last thing you can do at the command line, and Jean-Luc mentioned this as well, is you can bring to bear other Unix tools. So I was outputting things. So here's an output file. So here I'm doing looking at the network connections and exactly what was sent and received. And I was doing things like, let's grep for the 502 errors. Oh, there weren't any in there. Grepping for the word error. I can output it to a file. I can run awk sed. So I can bring to bear a lot more tools and do some more ad hoc analysis. I can also do, while I'm here I noticed, and do spectrograms. Notice the way I'm doing it, I like to put the chisel at the end, because then I can go up arrow, control W, and then just type in a new one, like subsec offset. And it's just quick in terms of keystrokes. Subsec offset is a chisel I added a while ago, or it's probably been improved since then. It's really nice to just be able to run it. Pretty cool stuff. So I'm going to go through some commands that are like that. You run them at the command line, and by running several commands, you can build up an investigation that's in your scrollback buffer, and you can refer to and copy and paste. So the first template is per event output. Sometimes the tool I'm creating, I would like it to have a per event, a total dump of all the events that happened. And then I can look at it later. That's good for workload characterization. I can also feed that into other tools. I might be grepping for things or frequency counting things. There's an example, OpenSnoop, which I've implemented many times. In fact, in Sysdig, it's a one-liner, just to show what files the open system call is operating on. You'd be surprised at how many times I've done this and solved a problem, because an application is looking for a config file in the wrong location, it's trying to open something in the wrong location, and you can see it straight away. A similar tool is filtered event output. This time I want to see per event, but only if it's based on some filter. I find my slower tools really useful. So I have things like file slower as a chisel, which will only print, I think I borrowed the older version, it will only print events that are slower than a provided threshold. So only show me file access slower than 1 millisecond. And I've also done these in other traces for, say, the ext4 file system and ZFS and ButterFS and so on. Great for proving and exonerating performance issues. Some people say, my application is slow because I have slow disk I/O. I can run file slower and immediately prove whether you have slow I/O that's causing application pain. Interval summary is another template that might be a little obvious. So tools like VMstat and IOStat do interval summaries, and we can do them in tracing tools as well. And I saw there are some Sysdig chisels for this, for doing, say, network throughput, and it'll do the summary. It's another template, and it can be appropriate for the tool at hand. That one is a tracing tool that's doing the directory cache stats, so references, slow misses, and so on. Count summary is another template I use quite often, and that's for looking at a frequency count based on a key. That example, I'm using func count, and I'm looking at the functions that began with VFS, and it's just doing a kernel frequency count. We saw some of them earlier today for Sysdig as well, and on the third lab, I'd solved it using the top syscall Sysdig, so that you could see that the closed system call was called the most. It's just another template, appropriate for the job. There's histogram summaries is another template I'll use. And that's where I'm interested in the distribution for a metric, usually latency. And I've done these many times before. That's biolatency. That particular example is has a normal distribution, but often these are bimodal, which is quite interesting to know. Then when you want to see the histogram over time, you can use a heat map or a spectrogram. And so that example is from Sysdig, and that's where you can imagine a histogram, turning a histogram into a single column or row of colors, and then picking the color saturation, including the hue, based on the value. And this is great because I now get to see how the distribution changes over time. This is the sub-second offset heat map or spectrogram, which is one I created, which is very strange, but it has a purpose. What it does is it shows when events happened in the offset of a second. And so you can imagine I'm drawing a row for each second. If I'm looking at a particular event, I can see, did it wake up at the same time every second? If so, I would have a vertical stripe. Did it wake up, do a little bit of work, and then sleep for an entire second? But then, as time goes on, wakes up at a progressively later offset of the second. And you can see those diagonal lines happen in that case. What if an application woke up every 5 seconds? We can see the 5-second dots as well. Interesting visualization. Gives you an insight into how application timing may be working, and also of the arrival distribution. Does work all arrive at once? So whatever this workload was, a lot of the events would happen in one large group, and then we'd go to sleep for the rest of the second, and then wake up again, and that would slide over time. So those are the different templates, and I'll put these slides on SlideShare. Now, about creating the tools, I've gone through some methodologies to think about posing questions, templates for creating different command line tools. Now I want to talk about the style and decisions for those. I like the tools to be valuable. So I've created these tool diagrams in the past for Linux, which are fairly popular, but it's something that I do study a lot of. What is the current landscape for Linux performance analysis? I end up using all these tools. I'm a bit of a tool nerd. And then by understanding that, I also know what doesn't exist. It's very easy with tracing tools to reinvent the wheel, since there's so much information. If the kernel already has some counters built in, I'd rather use those because they're probably going to be cheaper than having to fire up a tracer and do it. So know what already exists and what doesn't. Another aspect to describe is a characteristic to look out for is overhead. Tracing tools are often used, I'm often using them for performance analysis. Tracing itself can be dangerous. The overhead is usually relative to the event rate multiplied by the tracing event cost. Adam had a slide earlier today about how strace, the current implementation of strace, is violent and uses breakpoints and can really slow down an application. As an example, I've got how Sysdig works. The Sysdig driver creates a ring buffer so that our Lua chisels can asynchronously read at a much lower event rate, much reducing the overhead of this. And so the times I've tested it, Sysdig is like 20 times lower overhead than strace. But there's still overhead. And one of the challenging things about using tracing tools is having a good feeling of what the overhead is going to be and when it's safe to do something and when it's safe not to. You get pretty good at knowing the frequency of things. For a lot of tracing tools, if you're, with the exception of like strace, if I'm tracing something that happens at less than 1,000 times a second, the overhead should be negligible. If it's less than 10,000 times per second, it may be pretty hard to measure. If the event rate is over 1 million times a second, I'm probably going to be able to measure that overhead of the tracing tool. So you get an idea of what has different event rates. If it's disk I/O, unless you're a storage array, disk I/O shouldn't have a high event rate. And you can use I/O stat just to double check on production servers. So maybe you're doing 100 I/O per second on a server. That's going to be negligible to trace. File system I/O, that's going to be a lot higher, as your application will often hit out of the file system cache before it gets to doing disk I/O. And so it's something you might want to check, but if I'm tracing file system I/O, maybe that's doing 1,000 events a second, 10,000 events a second. It depends on the application. And that can get into the territory where the overhead will start to cost in a measurable way. Scheduler events for the kernel. So every time the kernel does a context switch, that can have a really high overhead. That can happen over 1 million times a second. Per packet events. Would per packet be high or low overhead? What do we think? High? If I'm doing per packet. Per network packet? Some people. What about low? Who's up for low? Nobody? It depends on the application, but packet rates can get really high. So if you're on 10 gig networks, you can easily get to 1 million packets per second. That's actually something that's valuable for moving closer to the application. If you trace at the TCP level, the event rate can be lower because TCP is operating in buffers, which then gets split on MTU down into the packet size. And so times I've tested, I've had a 3x delta between the packet rate and the TCP event rate, which means it's cheaper to trace at the TCP event rate. If you keep going to the syscall layer, it should also be cheaper, which is what, say, Sysdig does. Your application may be doing 1 megabyte writes to a network socket, but at the packet level, it has to split them into 1,500 sized MTUs. So you can imagine any tracer where you're operating at the packet level is going to have much higher overhead than if you go up stack and go to, say, the syscall layer. It's these sort of thought processes that will help you design good tools. Think first and foremost, what is the frequency of events I want to trace? And also to look for, is there a way I can solve my problem with a lower frequency event? So as an example of that, recently I wanted to know the the throughput of TCP sessions on service. And so I initially started by tracing send-receive, TCP send-receive. Not as bad as packet send-receive, but then I found out I could do the same by just tracing TCP set state, where it's the change of TCP session state, which is a much lower frequency event. So when you're changing from, say, send-receive to established or established to last stack, and then I can actually pull out throughput statistics from the kernel. And so I've gone through this iterative process of I can do send-receive, but how can I make this faster, and what's a lower event rate? You can actually imagine doing that at the syscall layer as well, where maybe I can do this just by doing the connect and accept, and when we close that file descriptor, instead of having to touch send, receive, and read and write. I also say design for low overhead and document expectations. And so a lot of my tools nowadays, I will, in the man page, have a section on overhead, and just state clearly, this is what the overhead should be. You may have a tool that does have a high overhead, so long as you warn people about it, they can operate with that. Like my strace one-liners, slow the target process and do this. Documentation. I think good tools have 3 docs: the code comments, a man page, and examples file. So the code comments, obviously for the next person who's reading it, a man page is a nice way to summarize what the tool does, to have a synopsis and an abstract, to talk about columns and switches, and then an examples file to... I really like examples files. People learn tools often by looking at screenshots, and this is also a testament to tool design. If you design a good tool, then I can look at the screenshot and then I can understand what that does. And so a lot of the tools I create, I will deliberately create a text file of example screenshots because I know it's a quick way to learn what the tools do. And I think I've probably got some of them sitting around, like... So my BCC tools. So it's just a text file that says, this is demonstrations of this tool. Here's some output. And then completely explaining it so that if someone's really new to this, then I haven't left a detail out. And just going through examples and examples and examples. So I'm a big fan of... This is one of many toolkits I've created. And I've got tools, and then I've got example files sitting next to each other. Every tool I write has an example file and a man page. Concise, intuitive, and self-explanatory. It's nice to have tools that don't have any clutter, don't have any unnecessary detail. Here's an example I like, I/O latency, and it only says what I need it to say. There's no wasted text. It's also intuitive. It's showing me a distribution, and it says that. It shows columns are labeled, so millisecond ranges. And I've got this sentence at the start, tracing block I/O, output every 1 second, Control-C to end. So the output is self-explanatory. You know what the tool is going to do. When I'm creating tools, you can also think of how would they look if these were in a textbook or if these were in a slide deck. Is there any wasted space? A lot of my tool outputs, they're very easy to put into slides because I just stick to the the exact content necessary. I also follow Unix philosophy to do one thing and do it well. And there's a case for multi-tools, and I've written some multi-tools, but I also like to have the single-purpose tools. I mean, you can think of OpenSnoop as a pretty single-purpose tool. It just traces open syscalls. ExecSnoop is another example of a single-purpose tool. I also like to make sure the output is less than 80 characters wide. And this is something that I'll fight over very fiercely. It's not just because that's the minimum size of terminals. With the output, in terms of helping tools get adopted, people will put your output in slide decks like I have, in books, in blog posts. And if you have that tool that has the 130 character wide output, it actually causes everyone a headache. Like, maybe that fits, but maybe it's going to cause problems when people are formatting it. It just makes life a lot easier if it's unnecessary to make it that wide, make it fit within 80 characters. And then that screenshot can get copied and pasted around a lot more. POSIX-style arguments. I really like my tools to have arguments that follow the same theme. If a tool does one thing and does it well, but I don't have weird arguments that completely change the behavior of the tool. And so here's biolatency, so I can add timestamps, I can change it to be queued times, I can change the units, but that's about it. You can imagine a tool. It's pretty easy when you're writing these tracing tools to say, well, the tool can do summary output, but I can have a switch and it would do per event output. And I find those tools more complicated to use. I like to keep them separate. So if you have a summary tool, it's a summary tool. And if you have a per event output, it's a per event tool. We've seen some of this today with the Sysdig tools, how there's clearly summary tools like top, prox, net, and then there's the per event output tools, which I think is good design. Also, think about the arguments and what would be ideal. Like, when I design tools, I really sweat very carefully about getting this as perfect as it possibly can be for tools that I'm publishing. So if I'm running a tracing tool that I'm going to use internally, and it's a hack, but I need it quickly to solve a problem, that's okay. But if I'm publishing it to share with other people, I really want it to get it perfect. And for there not to be a single character out of place in the output, or any dumb option, or any unnecessary option that makes it more difficult to learn. And one way to think about this, I guess, is the ping command. And some of you may know this story. Mike Muss, who developed the ping program, did it in one night. So he saw ICMP had echo request and echo reply, and thought, wouldn't it be cool if I could have a Unix tool that did this to find out whether another machine was alive or not? So he wrote it in one night and then shared it, and he later said if he had known that ping would be the greatest accomplishment of his life, he would have spent more than one night developing it. He would have added a few more options to ping, right? He said he was insanely jealous when a little later on, Van Jacobson did spend some more time on that, and Van Jacobson realized the trick of incrementing TTL so that as they expired, he could come up with a traceroute program. So if Mike Muss had actually stopped and thought about ping for a few more days, it may have actually had a traceroute option, and these wouldn't have been separate tools. Although it's probably a good thing they're separate tools because they do kind of do different things. But yeah, I try to think a lot about the tools and to get them really perfect. In my slides, which I'll share, I do have a table of POSIX-style arguments. So things which are conventions that I follow. Testing. I spend a lot of time testing tracing tools. I spend more time testing them than I do writing them. And it's I think if you can't write the workload, you can't write the tool. I do see from time to time people want to write a tracing tool, but they don't quite understand what it is they're tracing. And it's really illustrative to write that sample workload and to then trace it. So if you have a known workload, like if you can create a prime number of events and inject that, then you can verify the output of your tool to see if it matches. So maybe that's 23 events. Testing can be more time consuming than writing the tool itself. So I spend much more time writing these tools than testing these tools than writing them. Automatic tool testing is difficult, as a lot of the tracing tools you may need cooperation with other hosts, network hosts, and coming up with a test bed to reliably do that where you can trace out the targets is a complicated problem. So I had some examples here. How are we going for time? I know we're running a bit late. What's the...
We got about 5 minutes and then a few minutes for questions.
Like 5 minutes, all right. So some examples here, but I've already had some example screenshots. So tools I like, get host latency, it's sparse, it just does what it needs to do. ext4 slower is similar to my file slower, where I give it a threshold, output fits within 80 characters, and it's a nice single-purpose tool. And biolatency is an example of doing histograms, another nice, concise tool. For GUI tracing tools, I want to quickly go through some visualizations so that you can see how tracing tools can move to GUIs as well. For a lot of us, this may be where you end up spending more time using tracing tools, even if you realize it or not. So if an application vendor creates a performance monitoring tool that's a GUI and you're using that on systems, you may have no idea that behind the scenes it's actually using some tracer. So as templates to think about, similar to my CLI tracing tool templates, there's event logs. And that example is from Wireshark. So something we might be quite familiar with, Wireshark doing tracing at the packet level. There's tables, which is another template. This one's a bit boring. It's just my Google Chrome Task Manager. But you can imagine using a table as similar to my CLI Summary, summarization tool. Line graphs is another visualization template. This is an ancient tracing tool that actually used line graphs, a dynamic tracer from the 90s. But maybe that has a role for the GUIs you're building. Histograms, similar to what I had at the command line with the distributions. This histogram is bimodal, and that's really valuable to investigate and to see, say, tail call latency and outliers. And then heat maps, which we've seen many times today already with spectrograms. This is a heat map that Adam and I worked on at Sun, and this one's showing disk I/O latency over time. I really like this one. I was doing an investigation of throughput to a storage array, and to find out maximum throughput, I lit up one disk, and then 2 disks, and then 3 disks, and then 4 disks. And so I lit up the disks every few seconds until I had lit up all disks with load. And when I looked at the latency heat map, it looked like a pterodactyl from the Atari Joust computer game. And so obviously I had to get a screenshot. But really interesting to see what happens as we cross different points in that workload. Going from 8 to 9 disks is where the beak becomes the head. And I had a SAS engineer explain to me why. It's because, that's because it's handled in this way, and now there's contention. And so each of these characteristics has a particular meaning. I've had someone complain about the heat maps that I've done at a conference to say that by revealing all this information, I'm making more work for performance engineers because now we're on the hook to explain them all. But I didn't create the pterodactyl. It's always been there. You just need the tools to see them. And so that's why I like spectrograms as well. It's the same thing. There's waterfall charts, just to include in my deck of visualizations for tracing tools. And that one's the classical looking at a website loading from its components. You can do directed graphs from tracing tools. And so that example is from Netflix, our Sol utility, where we can see what microservice calls it, what other microservice, but it's a visualization that can be handy for trace data as well, whenever you have a hierarchy. Flame graphs. Flame graphs are simply a visualization of stack traces. Now, flame graphs are great for sampling profilers, but I'm talking about traces, per event traces, and I use flame graphs to visualize off-CPU time. So off-CPU time is when you block on CPU and you wake up later. I can grab a stack trace that explains why I blocked, and then the time I was blocked. And so that example is off-CPU time flame graph for tar. You can actually see proportionally the time I spent reading from disk, reading directories, and so on. And then the last visualization is flame charts, which I wanted to mention differently. Flame charts are what's in Google Chrome DevTools. And they're different. Flame graphs have the alphabet on the x-axis, the population. Flame charts have the passage of time. And so if you're sampling stack traces or you're tracing the flow of something, you can plot that over time and see how it changes. So desirable attributes for GUIs, valuable just like the CLI tools, documented, and I think we can do a lot more of documentation in GUIs. Tested, real time, and dashboards is a big opportunity to support methodologies, and we do that at Netflix, where developers create their own custom dashboards to help step through a particular process of analysis. So I'll share these slides. They have my CLI templates, and they also have the GUI visualizations, and I hope you can borrow from them and create better tools, whether it's at the CLI or whether it's at GUIs, because I think there's a lot of opportunities. It's exciting to work with traces, and that's a quick tour of some of the things we can do. Thank you.
We've got just a couple minutes for questions. If anybody has them, we'll hand you the mic. Brendan, the audience is stunned. Here we go.
We have a question. Great.
So the question is, what's the difference from BPF project, or the BCC project, and Sysdig?
The question is, what's the difference between BCC/BPF and Sysdig? BCC/BPF it's been a project to provide programmatic tracing into Linux. And some of the new tools I'm developing are using it. Sysdig has a Lua-style interface and an interactive Sysdig tool. And there are points where they've been much more developed. And so there's a nice set of analyses you can do with Sysdig. How I see the difference, BCC/BPF currently are pretty good if you want to hack at a low level and get into different layers of the stack. Like I go into the kernel, into different areas that Sysdig currently doesn't instrument. Sysdig has quite an expressive one-liner syntax. And so I can do OpenSnoop as in fact, let me just show you the difference between them. So I can do OpenSnoop as because I was trying it earlier. So this is Sysdig, and this is BCC/BPF side by side. They're pretty much doing the same thing. That's Sysdig. It has a very expressive and powerful syntax, Lua-based. Here's BCC. Can do the same thing. The tool itself is 183 lines long, so it's not one-liner. It's more powerful. I've got more control over what I'm doing. Here I'm doing stuff in the kernel. So if you're a power user, you'd probably like to hack on this stuff. But it's also pretty hard to hack on this stuff. On the other hand, with Sysdig, you have a really nice, concise front-end language and a lot of documented chisels. So, but really the main things are, it's more powerful when I go into the kernel, but it's also much more difficult to use. Yes?
Hi. You mentioned that testing these tools is one of the bigger difficulties. Do you have any tips from your experience on how to properly test them?
The question is about testing tools, and I think I need to get better at that personally. Back when I did the DTrace Toolkit, I had someone do basically a smoke test where they would just run each of the tools and then see if they blew up or not. That proved pretty useful, but that's really step one in testing. I found it really difficult to be able to test tools that monitored system performance and to be able to separate that out from noise on the system. Until you get far too many false positives because other stuff was happening, cron tabs were kicking off when you're trying to test the tool. How can we fix that? I do a lot of manual testing, and for networking, it's problematic because I often need multiple hosts and I need to be driving workload. I guess my answer is I think it's something that we need to develop that I haven't been really good at, but I hope in the future we can come up with better ways to test these tools so that they don't break, because it's important. I mean, individually at like a language level, there's been lots of tests. So DTrace has a massive test suite, BPF has tests, BCC has tests. So we can test functionality for regressions, but actually testing the output of a, say, network monitoring tool and making sure that the kernel hasn't changed a code path and now we're missing some send receives. That's really tricky because it can happen.
All right, one more round of applause for Brendan, please. Thank you very much, Brendan.